Hello guys, welcome back. In the last video, we introduced the ggplot2's conceptual model and discussed how we can piece a ggplot2 plot layer by layer by specifying 5 grammatical elements for each plotting layer. In addition to these 5 grammatical elements, there are several additional grammatical elements that mainly work on overall styles of a plot. Although ggplot2 provides a reasonable answer to styles and formats by default, we may still want to customize them for each plot separately. Let's consider this heat map to set a stage for these secondary but still important grammatical elements. This heat map gives a graphical representation of population density in Hong Kong's 18 districts, and the polygons that represent the regions of these districts are created by the geopolygon function, which uses a set of map data to determine the shape of these geometric objects. We further map the data on population density onto the color aesthetic of these polygons to color them differently. Then we get this output. But what things are going wrong with this plot? The main flaw is the color scheme. The colors used in this plot are not natural for us to comprehend and interpret relative magnitudes of population density. The current color scheme uses different colors to represent different levels of population density. But in our mind, population density is a continuous variable, so the use of different colors could be difficult for us to infer their relative magnitudes when cross-referencing these colors. Second, the axis labels are unnecessary because a map can only use longitudes to denote different horizontal levels and latitudes to denote different vertical levels. Besides, the current aspect ratio is somewhat inappropriate for a geographic map. The legend also needs some improvements. For example, we could give a better title to the legend and arrange its keys and labels to make it more visually compatible with the main plot. We may also want to add a title to this plot and reverse the colors used for the background and the grid lines. That is, instead of a gray background and white grid lines, it is more natural to have a white background and gray grid lines. It turns out all these aspects can be customized by the corresponding secondary grammatical elements we are going to introduce. To improve the heat map plot, we use a scale function to specify how population density should be encoded in terms of the color aesthetic. Here we change the color scheme to a gradient of blue, using a darker blue to represent a larger value, while a lighter blue to represent a smaller value. And then we use a chord function to change the default coordinate system to a map coordinate system, which sets the aspect ratio of the plot to the appropriate latitude-longitude ratio. We further remove the axis labels and a plot title, and customize the location of the legend, as well as how the legend keys and labels should be organized. And eventually, we end up with a more intuitive and meaningful plot. This slide gives a summary of the secondary grammatical elements. In the conceptual model of ggplot2, scales are used to specify how to map values in the data space to values in an aesthetic space. like what we did for the color scheme of the heat map. And we also need Coords to tell ggplot2 how to translate the two position aesthetics x and y to a two-dimensional position on a plot. For example, with map projections, these two aesthetics become latitude and longitude. And we can use the seams to exercise fine control over the non-data elements of a plot, like fonts, ticks, panel strips, and backgrounds. And they help us make the plot more aesthetically pleasing. One additional element that hasn't been embodied by the previous example is facets, which are used to create conditional plots. So if we are going to have multiple panels or plots to show some relationship among different subsets of a dataset, we need this element. Next, I will discuss these elements one by one and give you some examples that exemplify their uses. The first secondary grammatical element I would like to discuss is scales, which control the mapping from data to aesthetics. Scales take your data and turn it into something that you can read, like size, color, position, or shape. Scales also provide the tools that let you read the plot. These tools are the axes and legends, which allow us to convert visual properties back to data. Formally, each scale is a function from a region in data space to a region in aesthetic space. And in ggplot2, we need a scale for every aesthetic used on a plot, and each scale operates across all the data in the plot, ensuring a consistent mapping from data to aesthetics. So when we write a line of code like this, what actually happens is a line of code like this. It would be tedious to manually add a scale every time we use a new aesthetic, so ggplot2 does it for us. Default scales are named according to the aesthetic and the variable type. For example, this means the continuous scale for the X aesthetic. This means the continuous scale for the Y aesthetic. And this means the hue scale for the color aesthetic. Hue is one of the main properties of a color. Here, the hue scale is used because the corresponding variable class is a discrete variable, and the hue scale is suited to display discrete variables. Although we can generate many plots without knowing how scales work, understanding scales and learning how to manipulate them will give us much more control. If we want to override the defaults, we'll need to add a scale ourselves. The use of the plus sign to add scales to a plot is a little misleading. We are not actually adding a scale to the plot, but overriding the existing scale. Here we use the scale functions for the two position aesthetics to customize the labels for the X and Y axis. We can also plot data with a square root position scale and a Brewer color palette. This slide gives you all scale functions we can use to customize different data aesthetic mappings. The component of the scale that we are most likely to modify is the axis or legend associated with the scale. They are collectively referred to as the guide. You might find it surprising that axes and legends are the same type of thing. But while they look very different, they both allow us to read observations from the plot and map them back to their original values. The difference is only in that axes calibrate the scales of the position aesthetics, while legends calibrate the scales of non-position aesthetics. In ggplot2, guides are produced automatically based on the layers in our plot. This is very different from base R graphics, where we are responsible for drawing the legends by hand. Automatic inclusion of legends saves our time, as guides are the component of the scale that we are most likely to modify. Next, I will show you how to modify some common elements with scale functions in detail. The first argument to the scale function, name, is used to specify the axis label or legend title. We can supply text strings or mathematical expressions enclosed by quote as the name argument. This is another example of a text strings, which includes this special character indicating a line break. Because tweaking these labels is such a common task, there are three helper functions that allow us to do the same thing while typing less. They are used for X label, Y label, and labels for all aesthetics, respectively. In this example, I show you two ways to remove an X label or legend title. The first way is to set the corresponding label to an empty string. This way omits the label, but still allocates space. The other way is to set the corresponding label to null. It removes both the label and its space. The breaks of a scale controls which values appear as tick marks on axes or keys on legends. Each break has an associated label, controlled by the labels argument. If we set labels, we must also set breaks. The following code shows some basic examples for both axes and legends. If we want to relabel the breaks in a categorical scale, we can use a named vector. Accordingly, the second key label is changed to A, while the fourth key label is modified to B. And we should quote the numbers so as to use them to identify the labels to modify. The limits of a scale controls the range of values to be mapped on the scale. It's natural to think about the limits of position scales. They map directly to the ranges of the axis. But limits also apply to scales that have legends, like color, size, and shape. For continuous scales, limits is specified by a numerical vector of length 2, representing the upper and lower limits. In this example, because we set the limits to this range, the values that fall outside this range will not be mapped to this color scale. That's why we have some points colored gray in this plot. We can override this with the OOB short for out of bounds option to the scale, and color those out of bound values with the extreme colors of this scale. For discrete scales, like the hue scale here, limits is set by a character vector, which enumerates all possible values. And because here I only enumerate 2 values among all possible values of z, only the observations corresponding to these 2 values are colored in this plot. Again, because modifying the limits is such a common task, ggplot2 provides some helpers to make this even easier. The next 2 slides summarizes ggplot2 scales in terms of aesthetic and variable type. For example, there are 3 scales to map discrete data to colors. They are hue, blur, and grain. This table also lists some special arguments noteworthy for the corresponding scales. Some discrete scales for aesthetics like light type, shape, and the like are just a list of valid values in the aesthetic space that are mapped to the unique discrete values in the data space. They basically have no options. If we want to customize these scales, we need to create our own new scale with a variety of manual scale functions. Manual scale functions have one important argument, values, where we specify the values that the scale should produce. It usually takes the form of name vectors and match the values of the output in the aesthetic space to the values of the input in the data space. This example demonstrates how to use manual scales to customize the light type and color aesthetics. As you can see, these named vectors match the values of output on the right to the values of input on the left. All right, this is all for scales. The next grammatical element I'll talk about is facets. Faceting generates small panels, each showing a different subset of the data. It is a powerful tool when investigating whether patterns are the same or different across conditions, and provides an alternative to displaying categorical variables on a plot. To create facets, we need to specify which variables should be used to split up the data, and how the resulting facets should be arranged. There are 2 types of faceting, grid and wrapped. The wrapped faceting is created by the facet wrap function, which makes a long ribbon of panels and wraps it into 2 dimensions. This is useful if we have a single variable with many levels and want to arrange the plots in a more space-efficient manner. And we can control how the ribbon of panels is wrapped into a grid with the n-colon or n-row parameter. And the variable used to split up the data is specified by a formula argument. In this example, the class variable is chosen to split the data. And because it has 6 distinct values, we end up with 6 panels. And these 6 panels are arranged into a grid of 4 columns. The second type of faceting is the grid faceting, which is created by the facet grid function. The facet grid function lays out plots in a two-dimensional grid, defined by variables which form the rows and columns. The faceting rule is also specified by a formula argument, with the variable on the left-hand side of this formula determining the number of rows, and the variable on the right-hand side of this formula determining the number of columns. Both facet wrap and facet grid have the scales parameter that controls whether the position scales are the same in all panels or allowed to vary across panels. By setting this scales option to 3x, this plot uses different scales for the x-axis to display data in these 4 panels. To facet continuous variables, we must first discretize them. ggplot2 provides 3 helper functions to do so. In this example, I use the cut width function to discretize this continuous variable by dividing the data into bins of this width. And this can be verified by interval displayed at the top of each panel. Here, I also set the scales option to 3y to allow these panels to have different scales for the y-axis. The next grammatical element I'll talk about is coordinate systems. A coordinate system maps the two position aesthetics, x and y of objects, onto the plane of a plot. While the scales control the values that appear on the axis and how they map from data to position, it is the coordinate system that controls how the axis and grid lines are actually drawn. Although we normally use a Cartesian coordinate system, a number of others are available. They can generally be divided into 2 categories: linear systems and nonlinear systems. Linear coordinate systems require a fixed and equal spacing between values on the axis. That is, the graph draws the same distance between 1 and 2 as it does between 5 and 6, and they preserve the shape of geoms. In addition to the default Cartesian system, there are the flipped system, which exchanges the x and y axis, and the fixed system, which fixes the ratio of lengths on the x and y axis. On the contrary, nonlinear coordinate systems can change the shapes. A straight line may no longer be straight. The closest distance between 2 points may no longer be a straight line. A salient example of a nonlinear coordinate systems is the polar coordinate system, in which the position aesthetics x and y become angle and radius. Linear coordinate systems have parameters x limits and y limits. If you think back to our previous discussion on scales, you might wonder why we need these limits. Doesn't the limits parameter of the scales already allow us to control what appears on the plot? The key difference is how the limits work. When setting scale limits, adding data outside the limits is thrown away. But when setting coordinate system limits, we still have all the data, but we only display a small region of the plot. Setting coordinate system limits is like looking at the plot under a magnifying glass. This performs purely visual zooming and does not affect the underlying data. An important nonlinear coordinate system worth mentioning is the map coordinate system for displaying maps. Since maps are intrinsically displays over spherical data, simply plotting raw longitudes and latitudes is misleading. So we must do map projections with the map coordinate system.